Good afternoon, everyone. This is Team 1 for the flight control algorithm and claw mechanism for the Cal State LA Mini-Drone Competition. Our advisor is Ofelia Quintero, our sponsor is MATHWORKS, and our team members consist of myself, Rosa Cortes, our team lead, Rachael DiRegolo, Jonathan Caravantes, Isaac Aldape, and Cesar Chavez. Here's a quick agenda of what we will be talking about today. I will be talking about the introduction. Jonathan Caravantes will then be talking about the flight code algorithm. Rachel will follow by talking about the deployment. Isaac Aldape and Cesar Chavez will then be talking about the claw mechanism, and finally Cesar Chavez will be ending the presentation with the conclusion. So quick background, MathWorks is a corporation that specializes in mathematical computing software. Its major products include MATLAB and Simulink, which both support model-based design, data analysis, and simulations. The MathWorks Mini-Drone Competition introduced us to model-based design using Simulink. In doing so, we were able to learn more about certain drones. The other drone that we are working on is a Parrot Mambo Mini-Drone, which is also known as a quadcopter drone. Typically, these drones, they operate through a combination of technologies, whether it's computer vision, AI, object avoidance technology, and many more. Table 1 shows the two objectives that were given for this project. Their first objective was the flight code algorithm, which was to construct an algorithm that allowed a drone to fly autonomously from a starting position along a pre-described path using image processing. The second objective was a physical modification to the drone, which was to design and manufacture a claw mechanism that would enable the drone to pick up a package and return it safely to its initial position. The Parrot Mambo drone is a quadcopter drone that ranges from other mini drones. The hardware that was included in this given drone were an ultrasonic sensor, which is at the bottom of the drone, which is used to calculate the distance between a surface and a drone. There was also a pressure sensor and a battery that is about 3.7 volts, which is also rechargeable. The battery life of the drone itself is about 7 minutes. The battery life with the claw and the drone is about 3 to 4 minutes. The weight of the drone itself is 62 grams. The weight of the claw that will be used to pick up the Rubik's Cube that you see on the far right is about 12 grams, and the weight of the Rubik's Cube ranges about 12 to 14 grams. And now I'll be passing it on to Jonathan, who will be talking about the flight code algorithm.
The image processing block works by taking the video footage captured by the mini-drone camera and converting the RGB image into intensity. By doing so, it allows for the red in the image to stand out. Then, that signal is split in two. The top signal passes directly onto the edge detection block and is taken to the path bounding block. This signal will be used for the path detection algorithm, while the other intensity signal is converted into a double data type, then passed through the edge detection, where it will also go into the path bounding block. This signal will be used in the circle detection algorithm, as it outlines the shape of the circle more clearly than a non-converted signal. The path detection and centering, the non-converted vision-based data, is passed through a coordinate system function. The purpose of the function is to create an x and y coordinate system based on the number of pixels the image the drone produces, a 120 by 160 image. Then the coordinates are taken to the path centering function, in which it locates the edge of the path denoted by y1 and y2. And finds the midpoint of the path represented by y. If the drone deviates from the center, then the code will calculate the new distance from the edges of the path. This function will also determine if the track is angled or completely straight. Stateflow logic for path detection. The data values obtained in the path centering function will be fed into the stateflow logic. The drone begins by hovering over the track. Once the path is detected, the drone will then calculate to see if it is above the center of the track. Once it determines it is in the correct location, the drone will begin to increment forward. If the drone deviates from the path, the drone will recall the path centering function and correct itself. If the drone determines that the track has a turn, then it will calculate the angle of the turn and then yaw until the drone is facing in the center of the path. This logic will repeat until the drone finds a circle. Circle detection and centering. The converted vision-based data is passed through the circle detection and coordinate function. This function determines if a circle is present on the camera. If a circle is detected, then the code will find the center of the circle, denoted as C on the image. It will then relate the coordinates of the center of the circle to an x and y coordinate system. It will then determine if the drone is found horizontally or vertically above the center of the image. In this case, we use a range to determine the center of the image. Stateful logic for circle detection. Using the data obtained from the circle detection function, the stateful logic is only used once a circle is detected on the drone's camera. From then, it will begin to center itself above the circular landing pad until the center of the circle is found on what we determined to be an acceptable range for the center of the image. Once appropriately centered, the drone will begin the landing feature and terminate the simulation once it reaches the floor. The MATHWORKS simulation. The video that is being played in the background is the result of the mini-drone flying autonomously over a course with a total time taking 70 seconds. The drone starts by hovering over the course and then moves forward until reaching a turn. The drone takes the angle of the turn and determines which quadrant the angle is located, then yaws to recenter the path in front of it. From then, it will detect the presence of the circle landing pad, and once it's detected to be directly over the center, it will now begin to land. I will now pass it on to Rachael, who will be talking about the deployment for the drone.
Thanks, Jonathan. When we first tested our code on our drone, we found that the drone was crashing and not responding to the algorithm as shown in the Simulink simulation. To fix this, we needed to go to some simple testing to find out where the issue was. This video that I'll show here will test the connection between the computer and the drone, and if the drone is even able to process any type of code. The code that the drone's going to process in this video is a very simple code that commands it to launch to 0.9 meters and land after 5 seconds. There's no image processing or any large computations going on. So you can see that the drone responds well to the code and is able to launch, stabilize itself, and then land. Continuing, we needed to check if image processing was working properly on our drone. To do this, we tested the drone's response to finding and detecting a path in 2 separate ways. In the first video on the left-hand side, the drone is commanded to launch 2.9 meters and it will begin to move forward. When it moves forward, it's looking for a red color beneath it and its path. Once that path is seen, 5 seconds will pass and the drone will then land. In the second video, the drone is commanded to launch and move forward. Once the drone sees red beneath it, it's commanded to respond to that and land. Here you can see the drone launches and begins to move forward. It sees red and after 5 seconds, it lands. Additionally, the drone will perform a successful run. It launches and moves forward. It sees red and then it lands. It's important for us to note that the drone lands just behind the red path, that it sees red and the path in front of it. This is important for us to know and understand when we were writing our algorithm. Here we're deploying the code, our complete code, onto the drone. The drone in these 2 videos does not even reach the commanded altitude. It crashes before the code can even successfully deploy onto the drone. What's our issue? Why doesn't our code deploy onto the drone? From the trials that you've just seen, we have concluded that the hardware on the drone cannot process our algorithm. We say this because we've tested the connection between the computer and the drone working fine. We've tested that the drone can process and respond to a very simple algorithm that does not require any image processing or many computations at all. and we've tested that the drone can respond and recognize its image processing algorithm. With this being said, we can see that the drone cannot respond to the computations that we've written into our algorithm. Troubleshooting given more time, we would like to add time delays to test separate portions of the stateful algorithm. However, we have had some time to try to do this, and it has not been successful. This further confirms for us that our computations and our function blocks are too much for the drone to process. Given more time, with this being said, we would like to go into our code and rewrite some function blocks to try to simplify our algorithm computations and give the drone a shot at responding and deploying successfully. I will now be passing it off to Isaac and Cesar to discuss the claw mechanism portion of this project.
Thank you, Rachel. Now we're moving to the claw mechanism, the design process, and the first and last prototype that we build in this project. The claw mechanism is inspired by a bear trap mechanism, which is an entirely mechanical system. Uses a two-jaw system with a trigger that is activated by a torsion spring underneath and a pressure sensor that is, in this case, a lever. The use for this claw mechanism is a single load per use. Therefore, you need to reload every time you deploy the drone. The structure of the mechanism is detachable because we wanted an easy detach and attach the drone in order to change the pieces as we need it, or if one particular part breaks and we need to fix it or interchange to another claw that is functional. Major setbacks to this first mechanism that we designed, it was that because we got to design it before we got our hands into a drone, the measurements for the clip-on body and the size of every single component of this mechanical claw, it was an inaccurate measure. Therefore, it was not being able to attach to the drone, and some of the components were too small to even hold a torsion spring. Another setback is that the claw trigger mechanism was too small, as I said, and this also make this whole structure too weak to hold anything that we wanted to lift, particularly. The final claw prototype, or the current claw prototype, has still the same mechanism, and some of the similarities from the first prototype is that it's still a single use preloading, so therefore you need to reload it every time you use it. It is still a detachable clip-on body, but major differences were that we reinforced every single part of this mechanism. The base clips on perfect fit and is also a tougher design with a rounder surface because we wanted to be closer to the base of the drone. Also, we have a single point pressure sensor that has 1 foot on each of the claw instead of just one. We have a denser 3D printer pattern, and the trigger mechanism where the spring, the torsion spring, is going to be located is twice the size as it was before. As you can see in the claw components that we are going to see in this slide, in here we have the 3 different designs that we were progressively working on. The first prototype failed because the structure and the printing pattern was not too tough for the bending pressures, and it was also a fragile structure itself because it was a flat surface. And moving on to the last prototype, we had a much larger base. We had much tougher towers where the older components will be attached to, and also we have a larger space on the inside of the face in order to make the components larger itself. As you can see in this component, size changed drastically. The first prototype being a single lever mechanism, and the second prototype being a double ledge single eggshell movement that would hold 2 jaws in place instead of 1 as the first prototype. Also, the problem with this was that when the claw was activated or ready to deploy, the lever mechanism would only hold one of the jaws, which would leave the other one hanging on the air, while the second prototype holds both. And the pressure point, because it has a longer arm, it creates a more axial momentum. Therefore, it can't hold a larger pressure than the first prototype. But I think the spring trigger design is the most noticeable, that it changes from the first to the last prototype. The first prototype was a functional concept, was only made because we wanted to prove that the concept would work. We intended to be functional, but the trigger was too small to hold any commercial spring. Again, we tried different kinds of spring. We tried the bifold spring. We tried a pressure spring modified to be torsional, but still the size wouldn't allow it to function. On the last prototype, for example, we see that the size it's double the size on each measure. So we have enough force in order to apply a small torsion spring, and we found one that which its dimensions are 1 millimeter wire, 6 millimeter diameter inside diameter, and the torsion spring would create enough force to hold 120 grams from the claw without teeth. As you see here, the claw jaw mechanism changed drastically, and without need of explanation, it changed into a design that no longer required teeth, had an indentation where the pressure sensor mechanism would latch on in order to operate. And also, this new design was a little bit larger and tougher than the predecessor. And now we're going to move to Cesar to explain the FEA analysis and to show you some examples of the claw mechanism in action.
Thank you, Isaac. Now we'll be talking about some of the FEA analysis of the claw mechanism. However, before we get into that, I would like to talk about this picture. So here's a close-up image of the mini drone attached to the claw mechanism. The arrow indicates where the Rubik's Cube will make contact. And as you can see, the design, it's a fit tight and fitly seal, thanks to the base design that we have created on SolidWorks. As I mentioned in the previous slide, I will talk about some FEA analysis that we conducted on the claw mechanism. We have 3 different components of the claw mechanism broken down. And the left-hand portion is the spring trigger, and the right-hand portion is the jaw mechanism of the claw. And in the bottom left is the pressure sensor. So it is best to know that the blue indicates a low stress value, while the red indicates a high stress value. The arrows also indicate where the force is being applied once it makes contact with the Rubik's Cube. You are probably wondering, how did they create such a force and what force to be applied? Well, we are using a torsion spring. The torsion spring provides about 15 newtons of force. However, we wanted to make it a more realistic feeling, and we gave it a range about the 12 to 14 Newton force. We did not want to pass the max capacity of force that's provided by the torsion spring. In the next couple of slides, we will demonstrate how we have a fully functioning claw mechanism. Now we will be demonstrating in this video how the pressure sensor works once it makes contact with an object. Now I will be concluding the presentation. Now I'm going to wrap up the presentation with the conclusion. We were successful in the following areas where we were able to process an RGB input into a black and white binary image. We were also able to create an autonomous code that was able to center the drone above the path and also determine the angles of turn using an image processing feature. Finally, we were able to use a MATLAB function that was able to land in a circular path using circle detection. If we were given more time, the team would go back into the code and troubleshoot the problem so we could deploy the code into the mini-drone. For the claw mechanism, we were successful into creating a SolidWorks design and was able to print all the 3D parts and have a physical model in hand. The fully functioning claw mechanism only weighs about 12 grams, which is considered lightweight. And finally, the claw mechanism was able to lift up twice of the weight of the mini-drone, which is approximately 120 grams. The Castellet 8.1 mini-drone team would like to give thanks to the following people. We would like to give thanks to Ofelia Quintero for advising us and assisting us throughout the whole semester of our senior design project. We would also like to give recognition to Mike and Ray for providing the team with additional assistance and resource for our team. Also, we would like to give thanks to the MathWorks Corporation and the Castellet ECST department for designing this competition and providing us with this entertaining, challenging, and thought-provoking engineering problem. And most importantly, we would like to also give a special thanks to all the mini-drone teams for sharing their insights and for great progress. Thank you. This concludes our 2021 Expo presentation.